let's wrap up the groups on the periodic table. Group 17 is one of my favorites, the halogens. Group 17, let's look at their electron structures. Fluorine. Look on the periodic table. Fluorine's not super crazy, but I guess if I did do its noble gas shortcut, it would be helium, 2s2, 2p5. Chlorine. Chlorine, 17 electrons. So I'm going to go backwards to neon, 3s2, 3p5. Bromine. Bromine would be argon. Ooh, now interesting. 4s2, 3d10, and then back to the 4p for 5. And so on. This might give us a good snapshot. Valence electrons, or electrons in the outermost, the highest energy level. The highest energy level in fluorine is the second. We want all the electrons in the second energy level. There are 2 in the S, 5 in the P, for a total of 7. Then I go down to chlorine. Now we're looking at the third energy level, but it still has 7 electrons, 2 in the S, 5 in the P. Bromine. Now we're in the fourth energy level. And yes, there are some D's in the electron configuration, but they're in the third energy level. They're not going to be involved in bonding, because bonding and chemical reactions involve the outermost electrons. So now we're concerned with the fourth, or the highest energy level. There are 2 in the 4s, and there are 5 in the 4p. All halogens have 7 valence electrons. Cool. And now again, we kind of mentioned in the last video, don't say 5. It's not the highest energy orbital. It's the highest energy level that we're concerned with when determining valence electrons. All the electrons, regardless of the type of orbital they're in, we're looking for all electrons in the highest energy level. All the halogens should have 7. Now, their properties, they're interesting. They're very reactive. They're the most reactive. Nonmetals. None of them are metallic. They're all nonmetals, but they are highly reactive. Now, when we get to bonding, we'll look at the fact that stable orbitals are full. Atoms are really stable and they have full orbitals. Here's one of the reasons why these halogens are so reactive. Their orbitals are very close to being full. All we need is one more electron to fill that last p orbital. Done. They're very, very stable then. Well, if they only need one more electron to become stable, they are very, very reactive. Think about like sodium and chlorine. It's like a match made in heaven. You have sodium, one of the most reactive metals. The alkali metals are the most reactive metals. Chlorine is one of the most reactive nonmetals. Very common compounds, very stable compounds. I don't know, other things that are kind of interesting. This group starts off with fluorine and chlorine, which are both gases. Fluorine and chlorine are gases. Chlorine really is kind of like a yellow tinted gas. I have made chlorine in the lab. You can do some kind of cool reactions with it, but it's real irritating. It can be used as a disinfectant in solution. But the gas itself, this yellow toxic fluorine gas, that one's kind of irritating. So you got to do it in the fume hood, and even then sometimes you kind of still smell it. I'll show you some bromine and iodine. bromine is one of the two elements that naturally occur as liquid. It's really just bromine and mercury. They're the only two elements on the periodic table that are naturally liquids. And then finally you get to the bottom, iodine. We don't have any, but astatine. They would both be solids. What happens is these atoms get heavier and more dense as you go down the group. So you start on the top with gases. You have bromine in the middle, who's a liquid. And then finally down at the bottom, iodine, and again, if we had it, astatine would be a solid. The last group of elements on the periodic table. We've kind of worked with these guys. We should be familiar with the noble gases. The noble gases have full orbitals. They're very stable, which is why they are non-reactive gases. That's because they have full orbitals. I mean, they're all going to end with full S's, full P's, full D's, very stable, which is why they don't need to react with anyone else. Stable as they are. I guess one other little property that we could put down, kind of like the halogens, they do increase in density going down a group. We have helium. We do not have any of the other noble gases in our lab. We do have a helium tank. But I'll show you a video where you can notice that if you have a balloon filled with helium, it obviously floats. Balloons filled with like argon will kind of tend to hover in air. They have about the same density as air. And then as you get to the bottom, if you have a balloon filled with like xenon and radon, those balloons will definitely sink in air. Their densities do increase going down the group. And so we kind of mentioned this electron thing, that the electrons are all full in their orbitals. Well, yeah, as far as valence electrons go, helium. His configuration just is 1s2. Helium has 2 valence electrons. Valence electrons. Now let's go to some of the other guys. Neon, krypton. Neon. Obviously, I'm not going to do the noble gas shortcut. They are noble gases. Let's say 1s2, 2s2, 2p6. While we're at it, let's do krypton. Krypton, oh boy. Okay, I guess I could maybe shorten this up a little bit. What if I shorten this by, I don't know. Let's go argon. And then I'll say 4s2, 3d10, 4p6. I want to have some electrons showing, but I want to shorten it up maybe a little bit. Do we notice a pattern here? Something like neon. The highest energy level filled is the second. All the electrons in the second energy level are considered our valence electrons. There would be 8. I'm skipping argon, but if I were to go to krypton, same thing. The highest energy level is the 4th. There's 2 in the 4s, and there's 6 in the 4p, for a total of 8. All others have 8 valence electrons. Just not little baby helium. However, he does have full orbitals. He's only filling the 1s orbital with 2 electrons. He's very stable, non-reactive, full. Technically, helium only has 2 valence electrons. Everyone else will have 8. They'll have 2 in their highest s and 6 in their highest p orbital. Total of 8. Okay, so when we were talking about electron configurations back in the day, we said, helium's kind of got this identity crisis. We don't know where to put him on the periodic table. He's put in the noble gases because his properties match. Neon, argon, krypton, xenon, non-reactive gas. But technically he has 2 valence electrons, which is similar to the group 2 alkaline earth metals. But by no means are we saying that helium is a metal. There's another element that has a similar issue. Hydrogen. Hydrogen is a gas, but yet on the periodic table he's sitting up on top of lithium. Wait a second, that doesn't match up. Hydrogen is not a highly reactive alkaline metal, so why do we put hydrogen over in this area of the periodic table? Valence electrons. Hydrogen has 1. He has 1 valence electron, and hydrogen is actually pretty reactive. He's just not a metal, and he doesn't have some of those similar properties of the lithium, sodium, potassium. He's a highly reactive non-metal, but he does have a similar electron configuration. Hydrogen's electron configuration is 1s and a 1s1. Lithium will end 2s1, 3s1, 4s1, and so on. Now you might notice too, on some periodic tables, hydrogen is maybe like a little bit separated from lithium to show that he's put in this group because his valence electrons match up, but they'll separate him a little bit to show that technically he is not an alkali metal. Or like some periodic tables might put hydrogen in a different color to show too, like, okay, we get it. We're putting him in this first group, but he's not metallic. The properties are different, but his electron structure does match.